Okay, today we're going to be looking at change of direction of friction in different stages of motion. So let's consider the situation where we've got a shopping trolley and we're going to push, somebody's pushing this trolley in this direction, and then the shopper gives it a shove. So the trolley moves off, the handle on this trolley, in this direction. So what's going to happen after a few meters, the trolley will stop because of friction. So it's been given some force in this direction, but then friction, we call friction mu r, will act on it and it'll just come to a standstill. So after some time, our trolley is now sitting here and the only forces on it is mass and the normal contact force. Better put these on it because they're still on it even though it's whilst it's moving. So we've got this situation, and then it just comes to a stop. Now let's imagine the shopper does the same thing, but this time on a slope, which is a bit of a silly thing to do. But hey ho, this is what the shopper does. Trolley gets pushed up. It's meant to be a wee handle. So we've got mass mg, and then we've got the normal contact force, and it gets shoved up this hill, and we've got friction down the hill. Now obviously what happens, this is going to slow down. So we'll come to a point when the trolley is stationary on our hill. So we've still got, oopsies, that's a really, it's not a straight line at all, is it? But the mass, we'll have our normal contact force. There's now no force up the way, but we have friction still acting down the way. Now the question is this going to move? So if the slope is a very slight, a slight slope, then we could have the situation where the trolley just stops, and the weight of the size of gravity will not bring it back down. But say our slope is a bigger one, we are going to have the situation where normal contact force, where it's going to start to go down the hill, again under the weight of gravity, and in this case our frictional force will act up the slope. And so you see that in each stage friction is changing. When you're dealing with these sorts of questions, we need a force diagram for each stage of motion. So we need to be really aware of what's happening when, and when things change, and what forces are acting on our object at different stages of the motion. Now when you're doing these sorts of problems, we're going to be assuming that everything, that when we've got things moving up and down slopes, we assume that they're point particles, not a big shopping trolley. So our shopping trolley is going to be assumed to be a little point particle. And for the purposes of these questions, that is sufficient. So let us consider some questions. So we've got a box of mass 10 kilograms, and it's pushed from rest along a rough horizontal path by a horizontal force of 50 newtons. That looks a bit like the coefficient of friction, it's not, it's meant to be an N. 50 newtons for 3 seconds. The coefficient of friction is 0.45. Find the speed when it stops being pushed. So that's the first part of our question. The second part of our question is the box then slows down because of friction. Find the total distance the box has moved. So let's begin by doing our force diagram. So we notice that it's on a rough horizontal path and the force is horizontal force. So it's a path, it's not a slope, and it's on the horizontal. And we've got our box and it is 10 kilograms, so we've got the force of gravity down, 10g, and we've got our normal contact force, and we know it's been moved with a force of 50 newtons along the horizontal. So friction is going to be acting in the opposite direction, and that's going to be mu r. So let's resolve our components of the force. So we're going to resolve vertically first. So that will then give us r. So r must be equal to 10g because there's no other forces acting on the vertical. So r must be 100 newtons. Now we're going to resolve horizontally. So F equals ma, so the force is, we've got 50 in this direction, and in the opposite direction we've got friction, so that must be negative mu r, and that must be equal to the mass, which is 10 times a. So that using this, we then get a value for a, which is 0.5 meters per second squared. Now, with all of these types of problems, you really need to be careful to define the direction of motion. So this is our direction of motion. And just be careful with your signs. So now we can use our equations of motion to work out the speed when at the end of the 3 seconds. So we'll use v equals u plus at. Now v is what we want, the initial speed was 0, plus the acceleration is 0.5, and the time is 3. So this speed would be 1.5 meters per second. Now, the second part of the motion, the box then slows down because of friction. find the total distance that the box has moved. So the total distance is the two parts of the motion. So this is part one of the motion. So we can work out the distance moved in the first part of the motion. So we will use S equals ut plus a half at squared. So the initial speed was 0 plus a half times 0.5 times t squared, which is going to be 3 squared, which is 9, and that will give us 2.25 meters. So we're going to call this S1. Now let's draw a second force diagram for the second part of the motion. So still on our horizontal, we've still got our box here with the mass, the weight coming down here, 10g, and our normal contact force. Now there's no force pushing the box, but the box is still moving, so we've still got this direction of motion. So we've still got our frictional force in this direction. Now the vertical component is unchanged. R is still going to be equal to 100 newtons. Now this time the horizontal we've got friction must be the same as A. So A must be 0.45 times 100 over 10. Now remember, this is negative because the direction of motion is in this direction, friction's in that direction, so it's in an opposite direction, so it must be negative, and the acceleration will be negative because it's decelerating, so we have got minus 4.5 meters per second. Now we can use this to, again we can use our equations of motion. We're going to use v squared equals u squared plus 2as to find out a. So the final speed now is going to be 0. Our initial speed is going to be the same as the final speed here, so it's 1.5 squared plus 2 times minus 4.5 times s, which we want to find out. And then s is going to be, this is going to be the second part of the motion, so we'll call it S2. It's going to be 0.25 meters. So the total distance will be S1 plus S2, so 2.25 plus 0.25, which will be 2.5 meters. Let's do another problem. So now we've got a ball of mass 3 kilograms rolls up a slope with, oh dear, with initial speed 10 meters per second. The slope is at 20 degrees to the horizontal, and the coefficient of friction is going to be 0.3. So we're going to model the ball as a particle. So we're going to, and we want to find the distance up the slope when the ball comes to rest. And then we're going to show that after coming to rest, it starts to roll back down. And finally, we want to find the speed of the ball when it returns to its starting point. So, first part, we draw our diagram. So we've got our slope, and it's at 20 degrees, and we've got our ball, and it's got a mass 3, the weight's 3g, and we have our normal contact force, and then we have it's rolling up the slope. So this is our direction of motion. And therefore friction's acting down, so we're going to call it mu r. I want to know how far it will go up the slope. So we're going to resolve horizontally, perpendicular. Resolve perpendicular first, perpendicular to the slope. So r must be equal to 3g cosine 20. So think about a little triangle here. This is also 20 degrees. This is our 3g, and it's this part here which is perpendicular to the slope that we're interested in. So it will be 3g cosine 20, and that will equal our normal contact force, which must equal 28.2 newtons. So then resolve parallel. So we've got minus mu r, because it's down, and this is our direction of motion, and the component of gravity must be also negative because it's acting down the slope, minus 3g sine 20, and that must be equal to ma. So working all that out, we'll get an acceleration of minus 6.24 meters per second squared, which makes sense because the balls, if you were to roll a ball up a hill, it will go up and slow down until it comes to a stop. And we want to find the distance. So we're using our equations of gravity of motion. V squared equals u squared plus 2as is one we're going to use. the final speed will be 0 because it comes to rest. We know the initial speed is 10 squared plus 2 times minus 6.24 and times s is the thing that we want. So it, working all that out, rearranging everything, s will come out at 8.01 meters. Now, we want to show that after it comes to rest, it starts to roll back down the slope. So now we're going to do a new force diagram. So it's still 20. We've got our ball, it's 3G, and R's up here. And so if it's here, we've got a component of gravity pulling it down. So now friction is up the slope. So there's two ways in which we can now do this. So let's firstly resolve perpendicular. So R again must be equal to 3G cosine theta, which gives us 28.2 newtons, which is the same as before. Now we're going to resolve in the parallel. So this time we have our, so this time we're assuming that it's going to roll down. We're going to assume that it rolls down. So let's assume it rolls down the slope. Therefore, our positive direction of motion is down the slope. So that's really important to state. We're assuming that it is going to roll down, and if it rolls down, this is our direction of motion. So 3G sine 20 will be in this direction, and it must be, so we're going to use F equals ma, and so that's down, but this is up, so the friction is going to be in the opposite direction, and it must be equal to the mass, which is 3 and times A. So if we work all this out, we'll then get a value for A of 0.601 meters per second squared. Now, as the acceleration is positive, our assumption is correct. If we'd got a negative acceleration, then that would mean that the ball wouldn't be rolling back down the hill. So the positive acceleration shows us that yes, the ball does roll back down the hill. Now there's an alternative method. So alternatively, we can suppose the opposite. Suppose the ball is in equilibrium. So if we consider what the consider the parallel component. So F equals 3g sine 20, which is 10.3. So there's 10.3 newtons coming down the hill, but mu r, which is the friction, equals 8.46, and this is less than F. So this is not possible if the ball is in equilibrium. Therefore, it must be rolling back down. So finally, we are going to find the speed of the ball when it returns to the place that it started. So we try and squeeze it in down here. I'll just put a line here, because some of the stuff up here is what we need. So v squared is u squared plus 2as is what we're going to use. We want to find the final speed. The initial speed is 0, because when it starts up here it's 0, plus 2 times a times s, and we are using this value for acceleration, and s we worked out in the previous part of the question, so it's going to be 2 times 0.601 times 8.01, so that's 3.10 meters per second. So I hope that helps.